Hello physics students, this is Dr. Brenzy here, and this is lesson 7.1.2, and our objective for today in this lesson is that we're going to be able to define and calculate different types of what we call stress and strain on bulk objects. And what I mean by a bulk object is anything that just has volume. So an everyday object like a hammer or a basketball or anything like that that has volume is defined as a bulk object. So far, what we've done in physics is that we've treated objects as rigid. In other words, they maintain their ideal shape. But in reality, every material, no matter how hard it is, can really be squeezed, stretched, or twisted if you manage to apply enough force. Now, engineers especially are really interested in this. So when they deal with real objects that can twist or stretch or squeeze, then they have to calculate things called stress and strain. So today's topic is one of very huge importance to mechanical engineers and civil engineers. What is stress? Well, stress, in terms of physics, is defined as a force applied per unit of cross-sectional area. What do I mean by that? Well, let's say that we have a rod or a cable, and we decide to pull on this rod with a force F at each end. So we're trying to stretch this thing. And when we do that, we're applying a force on each end. And if we want to calculate stress, we have to calculate the force per unit area. And what we mean by area is this cross section. So you can imagine taking this rod or this cable and, making a slice of it, just like we do right here. And when you look at that slice, the area of that slice is called the cross-sectional area. So when engineers go to calculate stress, they take the amount of force that you're applying and divide it by this cross-sectional area, and that is what stress is. That is the definition of stress. The SI units of stress are what are called a Pascal. A Pascal is named after a French physicist named Blaise Pascal, who did a lot of work with not only, he actually did a lot of work with pressure. And you might have actually run into this unit in chemistry class when you were calculating pressure. And I'll explain how stress is related to pressure in a little bit later on in the lesson. But for now, let's just pretend that we have forgotten about chemistry, and let's say that 1 Pascal is equal to 1, this is the abbreviation for it. It's simply 1 Newton per meter squared of cross-section area. So if we were applying 1 Newton of force, and we were doing that with over a cross-section area of 1 meter squared, so this area of this circle be 1 meter squared, then we are applying a stress of 1 Pascal. Now, we really don't talk about stress without talking about strain as well. Now, strain is the material's reaction to stress. Now, if you took a piece of taffy, who eats taffy nowadays? I don't know, but if you took a piece of taffy or something else that was kind of stretchy, maybe a bungee cord, and you stretch it, you pull on both ends, you know that the length of that bungee cord is going to increase. It is going to stretch out by some length, delta L. Well, actually, every material does that to some degree or another. It's just that for some materials, we just can't see this very small change, delta L. Well, engineers sometimes have to take that into consideration, that things do stretch, all things stretch. So they define something called strain, and strain is the amount that the object stretched divided by its original length. So if it stretches a distance delta L, we would take delta L divided by its original length, and that would give us the amount of strain that the object experiences. Now you'll note, since we're taking units of length divided by length, strain is actually a dimensionless quantity. So if you were to tell me what the strain of an object is, you're not going to tell me it's something meters. You're just going to give me a dimensionless number. Now, in most everyday materials, if stress and strain are very small, which is the case for everyday objects like plastics and aluminum, well, maybe not plastic so much, but aluminum, metal, wood, those things, usually with everyday forces, the stress and strain experienced by objects is actually very, very small. Now, if it is very, very small, then we can say that the stress is proportional to the strain, or the strain is proportional to the stress. And they're directly proportional. Now, the constant of proportionality is what we engineers called a modulus. And that modulus is different for each material. So when you calculate, when you take the stress on a material divided by the strain it experiences, you're going to find that as long as both of these are small, when you take stress divided by strain, you're always going to get a constant for a given material. So let's say if you had a bar of aluminum and you stretched, you had a stress of 3 pascals, and you see the strain is, well, let's just say 0.01. You take 3 divided by 0.01, you're going to get 300. Now, if you were to take a different stress on that same material, like say, let's double the stress, well, what would happen is that the strain would also double, which means that this modulus remains constant. So this modulus is constant for a given material. So very often what engineers will do is they will look up this number for particular materials like aluminum or steel. They even have different types of steel because you can make steel with different alloys, which is basically different mixtures of materials. And engineers then look up this modulus so that they can calculate how much strain something is going to be under if you apply a certain amount of stress. Now for today, we're not going to talk about what that number, what small means. It's kind of a pretty qualitative description. Tomorrow, or in our next lesson, whenever that is, we're going to actually get into that a little bit more. What does it mean by small? And you'll actually see when this proportion holds up and when it doesn't. Okay. I do realize I'm going through this pretty fast, but I also realize that you can pause the video, so I don't want to spend too much time dabbling. So let's talk about different types of stress. Now I'm going to introduce 4 different types of stress. There's an additional one called torsion stress that I'm not going to get into today. I did talk about it, briefly introduced it before, but we're not going to deal with torsion stress in this particular lesson. So there are 4 types, however, that I do want to deal with. The first type we've actually already gone over is what's called tensile, which is another word for tension stress. So we know what tension force is that when a rope is stretched, it undergoes a tension force. So do other bulk materials like aluminum rods and other things like that. So when you apply a force over a cross-section area, you can calculate tensile stress when it's being stretched, and you can calculate tensile strain, and you will come up with a constant number for a given material, and we call that Y. And Y stands for what's called the Young's modulus. So the Young's modulus applies to tensile stress. We're going to get into other types of stress here momentarily. And for each different type of stress, it will have a different name for its modulus. So you got to get familiar with which modulus goes with which type of stress. So tensile stress is what's called the Young's modulus. Now another type of stress that you can put on an object is called compressive stress. It's the exact opposite of tensile stress. So instead of pulling apart, we are now pushing together. We are trying to squeeze these ends together and squish this rod or this tube, whatever you want to call it. Now, in most materials, the compressive modulus, in other words, the modulus we get as a result of taking stress divided by strain in compression, is equal to the same modulus in tension. So when you're dealing with compressive stress, again, you can use the Young's modulus. We don't have to have a separate modulus for most materials. Now, the exception to the rule is composite materials like concrete, which are like basically made of different rocks and mortar mixed in. So when you have a composite material like that, then your compressive stress becomes different than your Young's modulus. Or excuse me, your compressive modulus becomes different than your Young's modulus. But we're not going to deal with that in this particular lesson. So for us, we can just remember that whether we're in tension or compression, we're going to use the Young's modulus Y. All right, so I've gone through tensile stress and compressive stress. The third type of stress that we're going to talk about today is called shear stress. Now, you might remember this type of stress from our Lab 4 when we put our trusses under a shear test. Now, a shear test is designed to actually change the shape of an object. So somebody is applying a force at the very top of this material, and they are, in a sense, trying to, it's almost like a tearing motion. That's the best way to describe it. Now, if you think back to our Lab 4 experiment where we had trusses, remember that one of the tests we had a table, and we actually took our truss, let's say this is your truss, and we actually applied a force downward in this direction. Okay? Now you can think of this as a rotated version of this. You have, what's going to end up happening is that this truss is going to do something like this. Okay? So that's why we called it a shear test, because we were applying a shear stress to our trusses and figuring out what was the maximum amount of shear stress the truss could withstand. Now, shear stress, just like our other two types of stresses, are calculated by taking force divided by area. But, watch out, watch out, watch out. Danger, Will Robinson. The area that we are concerned about with shear stress is this area on top, where we are applying the force. We're not concerned about the area that we were for tensile or compressive stress. This is the area that we are concerned about. This is the area that we want to calculate. Right up here. Okay? So you could think of it as, what area is the force being applied on? Now you could imagine somebody taking their hand and just trying to smear this block toward the right. So really the force is being applied at the top of the block. And that's why we are concerned with this area and not the cross-section area like we were with other types of stress that we've talked about so far. It's a really, really important concept to understand. Oh, apparently I made two of those. Now strain, shear strain, again is a little bit different than the strain that we dealt with when we were talking about tension and compression. Now we know that this force that we're applying, that's smearing this thing to the right, is going to cause the cube, or at least the top face of the cube, to move a distance delta x. Okay. Now, when we're calculating strain, we don't take delta x divided by this distance up here. We actually take this height y. So y is the distance that we're concerned about with shear stress, or excuse me, shear strain. Okay. So with strain, you can almost think that the denominator, the directions need to be switched almost. Okay. The directions in the denominator need to be switched. They're not the same direction. This y is not going in the same direction as that x. Just like our area was not along the same direction as our force. I don't know if that thought is going to be helpful, but that kind of helps me a little bit. So maybe it'll help you too, but if not, find some way to remember that with shear strain, the denominator has to be the height, not the length. Okay. Okay, so we've talked about tensile stress, compressive stress, and shear stress, and now the fourth type and the final type I want to talk to you about is what is called bulk stress. So when you have an object that's surrounded by a fluid, in other words a gas or a liquid, that gas or liquid is going to press on every side of the material. And, excuse me, sorry, I had to pause the cough there. This force is going to be exerted on every side of the material. You can think of this as like pressure in a gas or a liquid. That's exactly what it is. So really, when engineers talk about bulk stress, you can think of going back to chemistry and thinking about pressure. So pressure is really the force per unit area pressing around an entire volume. Now, well, I was going to say something, but I decided not to do that. But okay. So, if, let's say, we have some block that starts at like a certain pressure P, and you know, virtually everything in everyday life starts at a certain pressure. Like even us, we have a gas around us, and it is exerting a certain amount of pressure on us. And that's something that you probably learned either in chemistry or in basic physics, or maybe even in science way back in middle school. So this block starts off with a pressure P, and then let's say that we decide to put it in some sort of chamber or put it in a tank or something like that that causes the pressure to increase. So now this object is under stress. We've changed the pressure by an amount P plus delta P, or actually we've changed the pressure by delta P. So we started off with this pressure, we changed it by this much. So we would consider the bulk stress as equal to that change in pressure. Okay, this is different than our other three types of stress, where we were just concerned about the total amount of force per unit area. Now when we're talking about bulk stress, we're considering the change in force per unit area. So that's something you have to be very, very careful about when you're dealing with bulk stress. Now, bulk strain, you could imagine that when this thing is out in air, in room temperature and stuff like that, it has a volume V. But then if we stick it in our tank and it undergoes a pressure P plus delta P, well, its volume is going to shrink because it's not an absolutely rigid material. Now, there's going to be a volume change equal to V minus delta V. So, when we go to calculate bulk strain of an object, we take the change in volume divided by its original volume, just like we would take change in length divided by original length for any of the other types of strain. So if I wanted to take bulk stress divided by bulk strain, as long as the bulk stress and the bulk strain are small, we can say that they are directly proportional, which means if you take one divided by the other, you are going to get a constant. That constant depends on the material that the cube is made out of. And this letter B, or this variable B, is called the bulk modulus. So we've dealt with 4 different types of stress and strain. We've dealt with tensile, we've dealt with compressive, we've dealt with shear, and now we've dealt with bulk stress and strain. And we've learned about 3 different types of moduli. We've learned about Young's modulus, which applies to tensile and compressive. We've talked about shear modulus. I don't know if I particularly mentioned that one, but that one's called shear modulus. It's usually a capital S. And then this one, bulk modulus, that is a capital B. So we have 4 different types of stress and strain, 3 different types of modulus. And I don't know why I put that up there a second time, but there it is. Okay, I want to finish up with an example here. A pretty simple one, and then we'll get into some different types of stresses and strains in class when we meet. So let's say I have a 3,340 Newton ball supported vertically by a 90 centimeter diameter steel cable. So it has a cross section that is a circle, and that diameter of that circle is 90 centimeters. All right. And for one, that's a pretty big cable, first of all. But, and then it's supporting a ball down here, and that ball exerts a force equal to m times g. So the force, that this ball exerts is 32,732 newtons. So I want to calculate, first of all, the stress that this force is causing on our cable. So, first of all, I have to identify what type of stress my object is undergoing. This is a pulling motion, a stretching motion along the long axis. So, the type of stress I'm dealing with is a tensile stress. So, before you do any type of stress or strain problem, it's really important to identify what type of stress you're dealing with. So, calculate stress for tensile stress. I just take the force divided by the cross-section area, since we're dealing with tensile stress. The force, the area, I can calculate just by pi r squared. It's the area of this cutout circle. And when I do that, I get an area equal to 0.636 square meters. So I'm going to take my force, 32,732, divide by 0.636, and I am going to get a stress equal to 51,000 something pascals. Okay, that was just the stress. Now I want to calculate the strain, but since I ran out of room, I need to go to a new slide, but you don't have to. Okay, now in order to calculate the strain in the cable, we know that stress divided by strain is equal to our Young's modulus. And we are given the Young's modulus for steel. It's 2.0 times 10 to the 11 pascals. So let's plug in some numbers. And let's go ahead and solve for the strain. And when I do that, I get a strain of 2.57 times 10 to the negative 7. And again, notice that there are no units attached to this because we are taking a strain is equal to a length divided by a length. So it is dimensionless. You might have noticed that this number is in pascals, that number is in pascals, so that number has to be dimensionless as well. Okay, so if I were just solving the problem, this is where I'd stop. But I do want to bring up a point in that, remember I said that these stresses and strains have to be pretty small. Well, that strain is really, really small, isn't it? It's 2.57 times 10 to the negative 7. Right. So let's just see how much this big cable stretches by applying this particular force over the length of the cable. So if I want to do that, I know that my strain is the change in the length divided by the original length. That's going to equal my strain. And then it tells me that the cable has a length of 10.3 meters. So delta L turns out to be 2.65 times 10 to the negative 6 meters. So this big fat cable, when you apply a force of 3,340 newtons, only stretches the cable a distance of about 2.65 micrometers. That's really, really small. But it does exist, okay? And you could imagine that maybe this starts getting important when this force starts getting really, really large. And that's why engineers have to know about this stuff. Because things do bend and things do break, right? And you have an example of that. Your truss broke, right? Yeah. Okay. So I look forward to talking to you in class tomorrow, and where we'll get some opportunities to look over Young's modulus, bulk modulus, shear modulus, and talk about stress and strain. All right, bye.